Next up, we are really excited to introduce a series of scientific talks. So we've already heard earlier in the day, AI innovation showcase from startups. And now we're going to hear directly from the researchers themselves what sort of really interesting projects they're cooking up in the scientific labs. So first up with my good friend and colleague and lab mate, Dr. Francois. Dr. Francois, MD, MPH, PhD, is a postdoc at Stanford for biomedical informatics research. He's a trained anesthesiologist and critical specialist all the way from France, with an MPH and a PhD in biostatistics from the University of Paris. His research focuses on building and evaluating clinical decision support systems using large language models and machine learning. He is especially interested in the real-world deployment of trustworthy, scalable AI tools in clinical settings, and his current work, which I believe is relevant to many of us in the audience, includes the development of an agentic hospital cost discharge summarizer, which is now being piloted at Stanford Center Hospital. Dr. Francois.
Thank you. All right, so let's start with a simple question, which is, what's the most fundamental challenge in healthcare today? Zach Kohani recently said, well, I'm hearing it everywhere, medicine is in deep trouble. So here in the US, we often talk about raising costs, insurance nightmares, equity and access, but this sense of crisis, it's also felt in the UK, in France, in Taiwan, it's everywhere. So maybe the issue is even deeper. And I think the core of the problem is this. It's the explosion of often hidden information that overwhelms human cognitive capabilities. We're just asking clinicians to manage more data than anyone can handle. And you see this clearly every day in one place. It's the discharge summary. Clinicians must sort through dozens of notes, understand them, and condense everything into something clear and accurate. It's a huge daily challenge. So clinicians often finish discharge summaries 2 or 3 days after the patient leaves, and that's a missed opportunity for good follow-up care. Doctors usually write the summaries late at night at home, what we call pajama time, and that's valuable time taken away from seeing patients, doing rounds, or handling hands-off. So I like how my collaborator, Dr. Jason Home, puts it. If we could generate high-quality hospital core summaries, we'd improve efficiency, patient care, and clinician wellness all at once. But generating text is easy, but how do we know if it's actually any good? So there are 2 main approaches, which are kind of opposites. So on one side, human evaluation, which is the gold standard. It's trustworthy, but not scalable. Every time you test a new prototype, you need a whole new round of human reviews. And on the other side, there's the pure CS approach, where you have an LLM judge the output of another LLM. And this is highly scalable, but it's not trustworthy enough for medicine. To fully trust this, we need to have access to sort of an Oracle-level LLM, which doesn't exist. Plus, there are known issues like LLM judges favoring formatting over content. So our question was, how can we get the best of both worlds? And so our insight was to split this problem in 2 sub-problems, where first human defines what a good answer is, and then we have LLM judges evaluate against that expert reference. Okay, so how does this work in practice? So this is where our pipeline that we call MedFactEval comes in. So first, for a sample of patients, we ask expert doctors to write down 3 key facts that they want to see in a good summary for each patient. And yes, it does take some human effort to build the data set, but it's a one-time cost that gets amortized over time. And here, it's really trust in the quality of the human labels that is key. Then for any generated summary, we use an LLM as a judge, and we can just simply prompt it with something like, does this generated text contains this important fact defined by physician, answer with an explanation in a JSON file, and we repeat this for every patient and every fact in the benchmark. And at this point, there's no more human cost, and evaluation becomes highly scalable. But to make sure our scalable evaluation pipeline is actually valid, we need to compare it directly to full human evaluation. And this is the platform we use. On the left, physicians see an AI-generated summary. And on the right, they they rate it on Likert scales for comprehensiveness, conciseness, and fluency. And that's our subjective grading. Then we ask them if the facts they find earlier for that patient, we ask them if they are present in the summary. And okay, so this was our pre-specified hypothesis based on early data. So as you see on the left, we expected LLM judges not to perform well on subjective grading because even human experts rarely agree on those. But for fact-based questions like, does this summary contain this key fact, we thought LLM judges would match humans much more closely. And that's exactly what we found. Fact-based LLM judges, they have about the same accuracy as a single human, but they're about 100 times faster and 10,000 times cheaper. So how do we actually generate these hospital course summaries? So for that, we use a pipeline that we called Med-Agent Brief. So for each patient, we collect all their clinical notes from the initial HNP to the latest progress notes, and we put them in chronological order. And these notes, they pass through a series of LLM calls and produce a structured summary. So we refine the format with a lot of feedback from our hospitalist colleagues. So the goal here is to automatically generate the summaries every day for every patient, let's say at 5:30 a.m. And these summaries, they can be used as a first draft to the discharge summary. They can be used as hands-off or to improve continuity of care. And I genuinely believe that these daily summaries like this, they can help make sure important medical information doesn't get lost in the flood of the progress notes. So let's look at an actual example from our generation pipeline. So each summary starts with a one-liner. So here it's acute kidney injury in a woman with lupus, end-stage kidney disease, and a kidney transplant. So this gives you the headline right away. Next, there is a one-paragraph overview of the hospital course, and then a highlight of any major outstanding issues. Then the summary breaks down by individual problems. For example, problem number 3 here is hypotension and possible sepsis. And every problem follows the same clear structure. So you have key diagnostic findings, therapeutic procedures, current clinical status, goals of care, outstanding issues. So this format keeps things clear and focused so clinicians know what to look for and where to find it. So our workflow supports HIPAA-compliant LLM. We currently use Gemini 2.5 Pro. But if something better comes out, like, I don't know, latent diffusion reasoning LLMs, well, we can easily switch. And each summary goes through a cross-checking step to reduce hallucination, and we include citations, so you see exactly where each fact comes from. So everything so far was done on past patient data, but to make a real impact, we need to generate summaries for patients who are still in the hospital. And for that, we teamed up with TDS here at Stanford, and we turned this into an AI care project, and the goal is to integrate our evaluation and generation pipelines into Epic using the FHIR API. And we've started working on this, and we plan to deploy our tool in the Division of Hospital Medicine at Stanford Sequoia Hospital this summer. All right, so how do we actually evaluate our summaries in the real clinical world without overloading clinicians? So here's the idea. So before seeing an AI-generated summary, we simply ask the clinician to write down 3 key facts that they expect to see. Then in the background, there's an LLM judge that checks, well, did the summary include those facts? Did it contradict any of them? And next, the clinician is shown an improved summary, one that includes any missing fact and some LLM-generated feedback. And finally, they can rate the revised summary on Likert scale and leave comments if they like. And we do this in this way for 2 main reasons. So first, it helps clinicians spot common AI failure modes, and it helps them learn how to better use the tool in the future. And second, and more importantly, we're contributing a real-world data set to MedHelm, which is Stanford open source benchmark. It's an initiative by Nigam Shah that's setting the standard for evaluating frontier models on real clinical tasks like this. So how do we evaluate summaries without, how can we measure impact from our tool? So for that, we're taking inspiration from drug development. So first, we focus on safety. We checked the factual accuracy using our scalable med-fact-eval pipeline. Next, we'll look at effectiveness. Here, our goal is to cut the median time from discharge to shot closure by half. Then we plan to scale up deployment and evaluate the tool at other hospitals. And finally, we'll move into monitoring, and we'll be watching for rare and long-term adverse events and track how our summaries affect PCPs and nursing home doctors who rely on them. And I'd like to thank our hospitalists and research collaborators at Stanford and all the TDS team for making this possible. None of this would have happened without everyone's support. And I think I'll stop here so we have time perhaps for questions. If you're interested in real-world deployments of medical AI tools like this, come talk to me. I'd love to connect. Thank you.
Hugo Decker in radiology. I would love this for the clinical reason for exam. So I will find you later and try to get it applied.
Yeah, maybe I can comment on this. So we focus first on hospital medicine, but clearly the goal after this is to scale up to other specialties. There's a question over there.
As someone in device development, I appreciate the drug discovery process evaluation. I'm curious about risk management, looking at additional mechanisms to deploy assessing failure modes. Like, how do you think about that?
Yeah, thank you very much. So yeah, this is a real, that's a huge problem because I think it's very hard to anticipate all possible failure modes from those AI tools that generate text because they have failure modes that are very different from humans, and we may be surprised. So for now, we just leave this door open with a framework where you can define, what a fact is. It's very general, but we'll have to, go through trial and error so we detect those, possible failure modes that we haven't anticipated. I think this is fundamentally a hard problem.
Any last questions? All right, round of applause for Dr. Francois, please. And I just wanted to thank you on behalf of all clinicians for solving such an important problem in discharge summary. I can safely say that's two headaches for doctors across the world, right? One is preparing a discharge summary, and two is trying to decipher what the heck the last discharge summary said. And so I think everyone can maybe start to see a bit of a theme emerging, right, around the importance of evaluations, whether that's across industry, whether it's across academia as well. So it gives me great pleasure to introduce our next speaker, Dr. Vicky Bikia, who's also going to be doing a talk on scalable evaluations. So Dr. Vicky Bikia is a postdoc researcher at Stanford University, jointly affiliated with the Institute for Human-Centered AI and the Department of Biomedical Data Science under the mentorship of Professor Roxana. Her research focuses on training and evaluating foundational models for healthcare, with a particular emphasis on multimodal modeling for patient outcome prediction in oncology. She also develops and assesses clinically grounded, patient-facing chatbots that aim to improve the accessibility and interpretability of complex medical information. Through this work, she aims to contribute to the broader goal of building trustworthy, equitable, and scalable AI systems that support decision-making in clinical practice and enhance patient-centered care. So we'd love for you to tell us, right, is evaluation just LLMs on LLMs and LLMs? So take it away, please.
Good afternoon, everyone. My name is Vicky Bikia, and I'm a postdoctoral researcher at the Daneshjou lab. Thank you, Ethan, for the kind introduction. And I'm really excited to be here today to talk to you about our recent work on a key challenge in clinical NLP, which is the evaluation of AI-generated text at scale. And specifically today, we're going to be targeting a high-stakes real-world application, which is the evaluation of hospital discharge summaries. So as already mentioned by Francois, evaluating clinical correctness in medical text is not just a technical task, but it's also a matter of patient safety. AI-generated text might read fluently or appear convincing, but when errors occur, the consequences might be serious. Until now, the gold standard method, like for evaluating the clinical factuality in this medical text, have been human expert review, which, however, is not scalable as it can be time-intensive, expensive, and often inconsistent. At the same time, recent advancements in NLP and generative AI have unlocked exciting opportunities as these models can interpret, summarize, and explain clinical texts. However, evaluating this capability still remains a challenge. Traditional baseline NLP metrics like Raoux or even Bear score cannot assess clinical factuality. There has been a significant body of research that tried to propose metrics that can solve this problem, that can overcome this limitation. However, many of them still are dependent on reference outputs or expert annotation or require external domain knowledge. That said, there is growing momentum. Initiatives like MedHome that have proposed a complete framework, leaderboard that benchmarks generative models in different clinical use cases, range applications from diagnosis, reasoning, to decision support. So these efforts are very important and very promising, yet we still need to dive deeper into the evaluation of long-form narratives like those of the hospital discharge summaries. So LLMs aren't really great at judging the truth. But what LLMs are really good at is generating text variation with fluency and nuance and strong domain alliance. So instead of asking LLMs to evaluate the accuracy of a clinical document, we flip the problem and we ask it to break it. And this is what we call perturbations. Perturbations are control label modifications that can include either hallucinated diagnosis, incorrect medication, missing follow-ups, timeline swaps, and many more. And because we know what's changed, we know exactly the type of the error and why it matters. So in order to scale this, we are proposing a perturbation engine to simulate clinical errors at scale. So our approach combines two complementary strategies. On one hand, we're having heuristics-based perturbations, which rely on rules-driven edits that can replicate common errors in clinical documentation. And this might include removing sentences randomly, shuffling sentences within text, modifying follow-up instructions, and many more. And on the other hand, we're having LLM-based adversarial attacks. This strategy taps into the generative power of large language models to create more variable and less predictable mistakes. And we group these attacks based on their severity. So by combining these two strategies together, we're able to create a rich spectrum of clinical errors, of simulated clinical errors that cover both deterministic but also adversarial edge cases. And here we can see a very simple example of such perturbation. On the top, we're having an excerpt of a discharge summary, and on the bottom, we can see how small parts of this excerpt have been modified. So this perturbation-based approach gives us something that has long been missing from the clinical NLP. And this is a scalable, domain-aware way to generate labeled data for training. By introducing all these clinical errors into the reference summaries or other clinical documents, we're able to create thousands of labeled data that can be used to train smaller models with fewer parameters, achieving faster inference, and finally, delivering a lightweight, deployable model that can flag errors in real-world LLM-generated clinical documents. In order to test this hypothesis, we evaluated our approach on one of the most important and challenging documents in healthcare, the hospital discharge summaries. But why discharge summaries are a difficult task? So discharge summaries can contain condensed information from 5 to 10 days of patient care, the entire hospitalization of a patient. They're in structure, they pull out data from multiple sources, they're very prone to errors. Actually, studies have shown that 25 to 50% of the summaries may contain errors. And these documents are not just for internal documentation. These documents are handed to primary care providers and specialists that rely on them for the patient treatment continuity, but also to patients that need to understand the care that they receive, but also to follow the instructions that are written in them. So in order to create a scalable and also structure evaluator for hospital discharge summaries, we introduced Safran. The goal of Safran is to provide a qualitative assessment through the form of an error analysis and a quantitative score, numerical value, when a comparison between a candidate summary and a reference summary is done. And in order to validate that, we use the MIMIC dataset, which is a publicly available data collection of the identified ICU discharge summaries that served as the reference for our perturbation engine. So specifically, we tasked our LLM framework to compare a candidate summary to a reference discharge summary, a perturbed summary to reference discharge summary, and asked it to generate a complete report including many different error categories that have been curated in collaboration with our clinical team. And here you can see more or less how the report will look like. The report will include all the different error categories in detail, together with the error counts and also the reasoning behind identifying these errors. And together also the matched clinical concepts between the two documents. In order to create also a quantitative signal out of this report, we designed a custom formula, which is called the Safran score, in which essentially in this equation, the different error types contribute differently to the penalty. So severe and frequent clinical errors reduce more substantially the score, while preservation of accurate relevant information is rewarded. And the final score is then normalized between 0 and 1, and this way it's interpretable, comparable across summaries, and also can be easily applicable in real-world clinical settings. And once now we're having a set of all this perturbation, we can convert these perturbations into supervision signals. So essentially, we start with a pair of a reference and a candidate summary, and we fit this for comparison to a teacher model, a larger model like Gemini 2.0 Flash in our case, and ask it to generate the Safran analysis, the error report. And we run this for all these summaries in our training dataset. And this way, we end up with a new training dataset that can be fed into a smaller student model, in our case, the Llama 3.28 billion parameter model, that is fine-tuned using LoRa. And this way, we end up having a deployed model, lightweight deployable model for inference. In order to evaluate how well Safran can generate outputs, we compare its output to the ones provided by Gemini. So here, to the left, you can see the distribution of the BERT score for semantic similarity. We can see that the mean BERT score of 0.74 was achieved, indicating that the Safran outputs are semantically coherent with the ones of the Gemini. And we ran this for 300 discharge summaries. And we also performed evaluation on a human preference data set where we asked clinicians, we gave clinicians with 2 candidate summaries and a reference one, and we asked them to decide which is the better one, the one that matches closer the reference one. And also the Safran preference was defined as the higher score achieved between the 2 candidate summaries. And we can again see that the preference is pretty aligned between the 2. And we also dive deeper by comparing the error counts as those derived from the 2 models, the Gemini and Safran. And again, we see a high correlation of 0.85. And I would like to conclude my talk by leaving you with a few takeaway messages. So the perturbation engine is the core part of our framework, as it injects controlled clinically meaningful errors into any reference EHR data, allowing us to create labeled ground truth data for training our models. Safran builds on top of this foundation and provides both a qualitative and a quantitative analysis using a student-teacher LLM evaluation. And together, these 2 components can enable scalable automated benchmarking of LLM-generated clinical text. And although Safran concept was built with discharge summaries in mind, it goes far beyond that, as it can be extended to any semi-structured, unstructured, or structured EHR data, enabling trustworthy large-scale deployment of Gen AI in healthcare, not only for validation, but mainly for patient safety. Thank you. And I would like to briefly mention that this is the result of a big team, and I would really like to thank all of the collaborators. Unfortunately, they cannot fit on the screen. So I would really like to thank them. I would like to thank you for your attention. I'm really happy to take any questions.
Hey, hi, Vicky. Thank you for the awesome presentation. How could something like this be used to help with patient health literacy, like translate it into ways that patients can understand their medical records? In addition to
in terms of patient literacy?
Yeah, patient literacy. Yeah, like patient health literacy. transforming it from something that helps providers to something that helps patients understand their medical records?
This is a great question. So a big part of our motivation behind this work is actually to be able to build patient or to evaluate patient-facing chatbots that can allow us to help patients better understand their medical information. So having this in mind, we are extending this framework to be able to evaluate beyond the accuracy of the summary per se, to also be able to evaluate answers provided by the LLMs regarding discharge summaries or radiology reports. So this is a very interesting orientation for our work. So as far as the perturbation engine goes, essentially the framework can be used as is, which is really exciting and allow us to already test the perturbation engine on different EHR data. Moving now to the Safran analysis, I believe that modifications pertaining to the specific clinical errors, for example, recognized within the report, will allow us to make more targeted applications on different clinical documents in practice. But I think that it's very promising and very easily scalable given the right clinical expertise and insights towards this direction.
All right, thank you, Vicky. That was an amazing talk. And I hope that everyone in the audience now has a good idea of how to deploy some of these scalable evaluation methods. And I'm actually really curious. So how many surgeons have we got in the room today? Can we have a show of hands? Right, because I'm here thinking, all the surgeons thinking, what's all this discharge summary, right? I'm not interested. I don't even write any discharge summaries myself. But it gives me great pleasure to introduce our next speaker, Dr. Xiaohan Wang. Dr. Xiaohan is a postdoc researcher at Stanford AI Lab, specializing in video understanding, multimodal foundational models, and AI for healthcare. He earned his PhD in computer science from the University of Technology, Sydney. Xiaohan has published over 20 top-tier papers in leading venues and has secured 4 first-place awards in AI competitions. He also serves on the program committees of major AI conferences and has been recognized as an outstanding reviewer at CVPR. So the surgeons in the room, this one is for you.
Hello, everyone. Thanks for the introduction. I'm glad to be here to introduce our recent work on AI-assisted surgery and surgical training. According to an analysis published in The Lancet, there are around 4.2 million people died within 30 days after surgery. This makes post-operative death the third leading cause of the total deaths globally. And this highlights how critical surgical outcome is to global health. Another clinical analysis shows the correlation between surgical skills and surgical outcome. We can see from this figure, surgeons rated as higher skilled by their peers have lower rates of complications and deaths. From this, we can see how important the surgical skill assessment and training in improving the surgical outcome. However, the traditional way of peer review-based surgical assessment and feedback is subjective, time-consuming, and not scalable. And this is where AI can make a transformative way. So what roles the AI can play for surgery? Here, we focus on 2 major opportunities. First is automated skill assessment and personalized training. We hope AI can provide automated feedback for surgical videos and also generate the score, the ratings to assess the surgical skills. The second is real-time situational awareness. We hope AI can provide context-aware guidance and also alerting in the operating room to provide some guidance for the decision-making of surgeons. However, several challenges remain. Given a surgical video, there are many fine-grained motion, and we need to capture this subtle surgical hand and tool movements to understand the surgical procedure. And also, the background changes and occlusions and extreme lighting conditions make it extremely hard. And finally, most important, collecting surgical videos and annotate them is very time-consuming. So how to train reliable models based on this limited annotated data is a very challenging task. To address this, we propose and develop a search match 3D framework. This is a joint work collaborated with Harvard Medical School, supervised by Dr. Brett and Professor Serena Yeung. In our pipeline, we try to understand who is performing the action, the operator or the assistant, and what they are performing and how well they are doing this. Here is the overview of our pipeline. We start from detecting and tracking hands with a vision foundation model. And given the output of the model, we can reconstruct the hand 3D mesh and project this 3D mesh to 3D key points. We built a model to learn the hand kinematics representations and try to apply this representation for downstream task analysis, like identify the surgeon's presence and like assess the skills and analyze the surgical outcome. Here is the results from our model. We can show our model can generate the accurate hand geometry even under like tremendous occlusions. And the right is the key point represented from the 3D mesh. These 3D key points can be easily utilized to build the downstream models. Here is the comparison with the previous 2D model. Without the 3D prior and the hand structure prior, the 2D model like underperform our model a lot. We can see our model can generate accurate and consistent, stable kinematics of the 3D key points. Like this set up a foundation for the downstream analysis of surgical trajectory, hand trajectory and kinematics. Based on the output of these kinematics, we train a model to understand the spatial temporal representations with the hand topology priors. Leveraging the hand prior, our model can efficiently leverage annotations and learn the effective representations. We apply the learned representations to understand the surgical role in surgical videos. Here we can see, like based on the trajectory, we can identify which hands is assistant and which hands from the operator. And from the ROC curve, we can see our model achieve a very high AUC score of 83%. And this analysis is very important to understand the surgeon's collaboration in the operating room and also to understand the workflow of a surgery. We also apply these representations to do automated scale assessment. Here, we generate a score for each surgical video, and we can see the generated scale score across different training level from postgraduate 1 resident to attending surgeons. The model assigns higher score to surgeons with great experience. This aligns with the clinical proficiency. And we are currently annotating the human rated score for each video and plan to conduct a more detailed regression methods for this kind of correlation understanding. Beyond just predicting a score, our pipeline can also provide actionable feedback with temporal grounding. So this is like the example of temporal grounding. Our model can generate the highlights across the timestamps for our surgical videos. So these highlights can show how the segment contributes positively or negatively to a final scale score prediction. And here is the example. The surgeons hesitates before the next move and need guidance from another expert surgeons. So the highlight is pretty low compared to others. Language is another very useful and valuable feedbacks. But beyond just predict the score, we need like more detailed reasoning trees for this score prediction. So we try to build a model to generate the video reasoning trees for this skill assessment. By this, we can achieve better performance and better explainability. Here is our model named Video Self-Training with Augmented Reasoning. We start from a pre-trained video large multimodal models and a set of videos with just course label, such as just the score and just the action classification labels. And we can generate the rationale for the question answering task and do label verification iteratively. And finally, we can get the video VLM with better reasoning capability and also all the reasoning trees for the training data. And our model consistently improves the baseline models on general video understanding task, video reasoning task, and skill assessment task. Looking ahead, our long-term goal is to develop the surgical copilot with real-time multimodal feedback in the operating room. So with this kind of surgical copilot, we try to make the AI as a meaningful, useful partners in operating room that can make surgery more safe and improve the surgical outcomes. Thanks for the attention.
Obligated to ask a question. So I really loved how you were able to kind of differentiate by PGY level as well as the operator versus the assistant. I'm curious, are you able to pick up switching of roles? Because in operations, sometimes the attending will be the assistant, but then have to change. And it would be great to provide feedback on the critical portions of the case for trainees, like when they're able to perform certain tasks and graduate from one responsibility to the next, because each procedure has multiple portions.
Yeah. Thanks for the great question. I think that's also the question I like. You're always discussing with my surgical collaborators. Like they care about the collaborations in the surgical, in the operating room, and also they want as our model can like segment the different like steps of a surgery, because like sometimes one like step is very critical for the entire like the surgical procedure. I think our model also can like generate the segmentation masks for the entire surgery. That's an ongoing work we are trying to do. Yeah, thanks.
Great. We have a question from online. This is from Raymonde Uy. At the end of the day, patient outcomes ultimately dictate surgical success. Are there plans to validate skill scores with patient outcomes across training levels?
Yeah, I think that's a great question. We collected around 300 cases with the outcome labels, but we found it's very hard to directly predict or correlate the representation or the prediction from the model to the outcome, because the patient outcome can be influenced by various facts, like the intrinsic condition of the patient, the time of the surgery takes. But we try to group this like representation and try to provide some new insights for the like cases with different outcomes. Thanks.
All very exciting. So how long do you think it would take until we see the first entirely robot, surgeon? How long is that going to take, and what's stopping it right now?
I think it's a long journey towards the ultimate goal, because like it's very hard, like compared to the general tasks. Surgery, like we spent 3 years to just recorded around like 2,000 surgical videos, and all based on this video to do the analysis. If we can get like much more data to train a surgical foundation models, and that maybe make the ultimate goal earlier to achieve.
Maybe just one day, just like the Waymos on SF, right? Stanford will all be robot surgeons, but still some time away because of data.
Yeah,
Gotcha.
That's also why we welcome like all the collaborators from the hospital, from the surgeons.
All right. Looks like we have any more final questions before we move on to the next panel, which I'm really excited about. All right. Thank you very much.
Thanks.
Xiaohan.
That's a good.